today's tutorial is about curve sketching. And in an earlier tutorial, I did some problems from chapter 6. So let me share my screen with this PDF. So this is page 153. And this is what I wanted to talk through with you today. Now, this is a tutor-led tutorial, so I'll be just working through the problems with you. But feel free to chat, ask me questions, get involved via the chat or however. Like I said before, if you want to look at solutions for chapter 6, I did those in Tuesday's tutorial, so you can check the recording for that. Okay, so I wanted to concentrate on chapter 7 today. So I thought we could start with question 3. Now, odd and even functions are really important for curve sketching because they help us predict what's going to happen, and they help us make our sketching easier. Okay, so I wanted to work through question 3, but before we do that, let's actually talk about what an odd function and an even function are. So let me share my document camera with you. Okay, so this is one of the ideas that I like to use when talking about even functions and odd functions. Okay, so the way that I remember it is that with an even function, you have this reflection in the y-axis. Okay, so there is a algebraic way of describing this. Okay, so this is true for all x. So basically, if you go here to the right, that should line up with the same distance in the other direction. Okay, so an example is something like x squared. Okay, that's an even function, and you just have this reflection in the vertical axis. Okay, the second part is an odd function. Okay, and so with this one, the way I like to do it is think of it like this, right? Let's say these are your original axes, and I've just drawn in the curve x cubed. Now, if I rotate my entire page, just looking at this graph here, I get the same function. Okay, obviously the axes are a little different, but I get the same function. So this would be my new positive x-axis, positive y-axis. So that's a quick check to see whether or not a function is odd. Okay, so in this case, it's this algebraic one, and an example is x cubed. Okay, so they're the ways I like to think about even functions and odd functions. Here we've got a reflection. Here you can just rotate everything 180 degrees and you get the same curve. Okay, with the new axes. All right. Okay, so let's have a look at some of these questions from the course pack, and yeah, we can look at odd and even functions. And some functions are not odd and they're not even. So yeah, so there's a third type as well. So let me go back to the PDF. So here it is. Suppose that f is an odd function, okay? Determine whether each function below is odd, even, or neither. So you've got a combination of things. All right, so let's see how we can work through some of these problems. Okay, so this is question 3. Let f be odd on the real line. That is f of x equals this for all values on the real number line. Okay, so for part A, let's have a look at this combination. All right. So we've got this combination of functions, which is basically a product of x squared with f of x. Now, I think what this question is trying to do is to get you to look at what happens when there's a product of two functions, okay? So this is an even function, and we know that this is an odd function. So what happens when you multiply an even function by an odd function? Does anybody know in the chat? Can anyone remember, or does it ring any bells? So an even function times an odd function. Who can tell me in the chat, does this have a special product that we can? All right, Tom says odd. It is odd, Tom, okay? So the product gives an odd function. Now, I'm not talking about odd and even numbers here. One of the, I have plenty of videos on YouTube, right? And I have a few videos about odd and even functions. And I say something like this: an even times an odd equals an odd. And the comments go, Professor, you are wrong. Odd number times even number does not equal an odd number. And I have to explain that I'm talking about functions, okay? So I'm only talking about functions here, not numbers. Okay, so this product then is actually G is an odd function. Okay, now if you wanted to test that directly, you could. Of course, you could. You could put in, consider negative and replace x with negative x and there, and you would algebraically get it, okay? So let's try that. So alternatively, let's consider this. So we want negative g of negative x, and we want to show that this is equal to g of x, and that'll also satisfy the odd condition, right? So let's make this negative, replace x with negative x, and we'll get something like that, right? Now, if I square negative x, I'm just going to get x. And what do we know about this? Negative f of negative x equals f of x. So that is just g of x. So that's the algebraic way, but this is a really nice, quick way, okay? Just understanding that when you multiply certain types of functions together, you can predict sometimes you can predict what's going to happen, okay? So let's try another one. Part B is this, okay? So now we have a situation where we've got an odd function multiplied by another odd function. So can anyone predict what this product might be? In the chat, what do people think? then it is, yes, correct, it is an even function. Okay, so this product actually will give us an even function. Okay, so let's just so if that's true, then G is even. So let's do it just the algebraic way. Let's really consider G of negative X, and we want to show that this is actually equal to G of X, right? So we go up here, we replace X with negative X, and we'll simplify. Okay, so this is going to be negative X cubed, and negative F of negative X equals F of X. All right, so we reach the same conclusion. Okay, so that's pretty easy, right? But the most important thing in my mind is really understanding these definitions and the symmetry and you know, in this case, the rotation, what's going on, okay? And then you can think about all the products and stuff like that. Okay, last one. Part C is the following function. Okay, so now we don't have a product, we've got a sum. So can anyone make any predictions about whether G is odd, even, or neither? Let me know in the chat. What do you think? Can we make any predictions about this? Tom and Isabella say neither. And you're absolutely correct. We don't know anything. Okay? So then we cannot conclude that G is odd or even. We don't have enough information. Okay. Let me just try this light. Ah, that's a bit better. Okay, so it's neither. We don't know. Okay, we don't know. Okay, so that's a little bit about odd and even functions. Let's have a look at parametric curves. Parametric curves are amazing. So let me go back to the PDF. And we'll move down to questions on 7.2. Let me just get my pages together here in the background. Yep. So parametrically defined curves, these things are amazing because this little parameter t allows you to do stuff that you can't do with regular functions. Now, believe it or not, you've seen these kinds of parametric forms when you have done algebra. And the parametric vector form of a line, for example, right? That is an example of a parametric equation. So you've kind of already seen these before, right? So sketch the curves, blah, 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 find a Cartesian equation. So each sort of variable here, x and y, depends on this parameter t. So what we want to do to find the Cartesian equation is to eliminate the t's, eliminate the parameter, and just get an equation involving x and y. Okay, did somebody say GeoGebra? Let's go to GeoGebra and we can see what these oh, hang on, I don't want to share that just yet. I'll go to GeoGebra. Yep. Okay, so let me make that a little bit bigger. All right, so what I'm going to do, let me move that over there. Okay, sorry, I've only got two screens here, so sometimes I'm a little bit trapped for space. Okay, so let me put in this thing. It's going to be 4 times cosine t, comma 5 times sine t. Okay, so let me go back there. You can see, you can get rid of this, that it's not quite a circle, but it's more of an ellipse. And what GeoGebra has done is sort of put it into this other format here. Okay. So one of the questions here is, what does T represent? Okay, what does T represent? Can anyone suggest what T might represent in this picture? Let me know what T might represent. Tom says the angle. Can you be a bit more precise, Tom? I think you're on the right track. Which angle? So I think you're on the right track. Yeah, that's better. That's a bit clearer. So yeah, if I say have a point here and I draw a little vector or a little line segment between that, then the angle, right, will be could be, you could describe the angle by this T value. All right, so we kind of know what it is from GeoGebra. Let's have a look at how we might do this algebraically. Okay, so let me share my document camera. So this is question, what question is this? Is it 7? Yep. Okay, so consider these points. So how might we get rid of the cosine t and the sine t? Well, one way to do it is to use cos squared plus sine squared equals 1. Okay, so let's isolate them and then we can use the well-known formula. Okay, so let's square this, add them together, and then we will get the following. So I'm going to square that. I'll get x on 4 all squared plus y on 5 all squared equals 1. Okay, so this is the equation of an ellipse. So you can see in this final version here, we've eliminated the parameter t. Okay. all right, let's continue on this path and we can do part B. Part B is, just close that, is the following. Here we go. All right, so now we have some slightly different equations. We've got 3 sec t and 2 tan t. So let's put that into GeoGebra. Let's have a look and see what it looks like. I'm just going to put this in the background. So let me just give me a second. Okay, so let me share that with you. So you can see here, we've got this hyperbola going down here, going down here. Don't worry about these straight lines. They're just for guidance, I think. So we have some idea from GeoGebra that this might be what's known as a hyperbola. But let's see what we can do algebraically, okay? Okay, so similar to the previous question, we're going to use a trig identity here involving sec squared and tan squared. So we have x on 3 equals sec t, y on 2 equals tan t, and we have tan squared plus 1 equals sec squared. So we're going to square that. Oh, okay. Oh, I've sort of put that over here, but that's fine. Okay. So we can expand this if we want to. Let's go, I don't know, x squared on 9 minus y squared on 4 equals 1. And this is a hyperbola. Again, you can see the idea was pretty easy there. We just used a trig identity to get rid of the t's. Now, it's not always possible to get this lovely cancellation or disappearance of the parameter. Okay, so I'll show you another one, and it's actually not possible to get rid of these things, but we can still work out what's going on with a little bit of help. Okay, so the next one is the following. It's a little bit more difficult. It's a product. For x, it's e to the t times cosine t. And for y, it's e to the t sine t. Okay. So what can we do there? Well, let me try this in GeoGebra, and I can see what it said. So just give me a minute. Okay, so here it is. Let me share that with you. All right. Whoa, we're zooming out. Whoa. Okay, so this hasn't plotted the whole curve, but it's plotted the first part of the curve. Okay, and it looks like it's starting to become a spiral, right? You can see it over here, it's just restricted the t values. Okay, so from GeoGebra, we would expect that this is going to be some sort of spiral. How would we do that algebraically though? Well, I'm glad you asked. So let me see what we can do with this. Okay, so where's my pen gone? Oh, there it is. Okay. So similar to before, we can use cos squared plus sine squared, but we're not really going to be able to get rid of the t very easily. So if we square both of these things, then we're going to get e, and I'm just factorizing here, e to the 2t cos squared t plus sine squared t. This will be 1. Okay, and we get something like this. Now, what does this tell us? Well, it tells us that when t equals 0, the square of the distance to the origin is 1, right? This, you can think of this as the square of the distance from any curve on the point to the origin. And as t increases, e to the 2t gets much bigger, right? So if you think of this as a sort of an angle here, what's going to happen is as we rotate, t increases and the distance gets further and further away. So it sort of gets big like that. Okay, and it keeps on expanding because as t increases, e to the 2t gets much, much, much bigger. So that's one way of understanding what's going on here with the curve. Okay. All right. Let me go back to the PDF. Yeah. So let's do some. So we know how to sketch these things. Let's do some calculus with these parametric forms. Okay. So I'll go back to my PDF. So here it is. And I thought we could do 8 part C. So for each curve given in parametric form, find the points on the curve corresponding to these things, find any point on the curve where y is 0, and hence find dy dx as a function of t. Okay, so in the chat, let's look at part C here. Who can tell me, what would you expect this curve to be? How would you describe this curve? Yeah, yep. Thin, can you say a bit more? It's a circle, yep. Unit circle, yep. Can you say even more? What about the center of the circle? Where would the center of the circle be? Yeah, that's it. Okay. So we kind of know what's happening with our curve, and the way that you can confirm that is just go, well, cos squared plus sine squared equals 1. So you'll get that out. Find the points corresponding to this. So you would basically just put in t equals -1 here, and then 0, and then 1, and then 2. Okay. So let's go through this, and we can work it all out. All right. So question 8C. Consider, please. Right? So we have x squared plus y squared equals this. So our curve is the unit circle. So by unit circle, I mean circle of radius 1 and center at the origin. Okay, so you can kind of think of it like this, and that's 1, that's 1, and the t here could be the angle down there to the positive x-axis. Okay, all right. So find the points on the curve corresponding to these things. So let's do. So if, say, t equals 0, then x equals cosine of 0, which is 1, and y equals sine of 0, which is 0. So you would just be here, right? You'd be at the point 1, 0. Okay, so you just make the other substitutions in the same way, right? You would put t equals -1, so that you get cos of -1, sine of -1. And you can relate it back to the circle just by looking at the angle in radians here. Okay, so I won't do all of those because they're pretty easy. Let's have a look at the points on the curve where y equals 0. Okay, so, all right, if y equals 0, it means that sine of t must equal 0. Okay, so that's the only way. Now, if we look at our curve, where is y0 equal to 0? Well, it's here, right? It's there, and it's there. Okay, so what will t be? Well, you're just solving sine of t equals 0. So it's true for this. Okay. So the 2 points are 1, 0 and -1, 0. Finally, a little bit of calculus. We're asked to compute dy dx. Okay, now because this is a curve that involves a parameter, we can't just go straight out and differentiate this. You could say, well, we've got this curve in here, you could implicitly differentiate that, sure, but I don't think that's the point of this question. I think what they want you to do is to use the chain rule here. Okay, so let me show you how we do that. So you can write this as the following combination. Okay, you can think of these dt's as cancelling and sort of behaving a bit like fractions. Okay, so if y is that, well, it's pretty easy to work out dy dt because I differentiate sine with respect to t and I get cosine t. And dx dt will just be this differentiated, which will be negative sine t. Now we're assuming here that this denominator is non-zero. Okay. All right. So what does this give you? Cosine on sine is cot. And there you go. Okay, it's a function of t, cot t. All right. Okay, let me have a look through this. Oh, we haven't talked about polar curves. Okay, it always sounds a bit cold when you talk about polar curves, right? Because it reminds me of the North Pole or the South Pole or something. But it's pretty easy, and it's something that you've already seen before with complex numbers and the polar form, right? The complex polar form. So let's just refresh our memory quickly about the polar form, right? So with the polar form, you don't have this x and y coordinate. What you have is this r and theta. Okay, so r is the distance from the point to the origin, and theta is the angle between this little line segment and the positive x-axis. And as you increase theta, you rotate anti-clockwise. Okay, and the basic connection between this and your Cartesian setup is this. Okay, so it's very, very similar to what you've seen with the a complex exponential form, things like that. Okay, so let's have a look at the PDF, and we can do some problems. Okay. All right. So 13. The following points are given in polar coordinate form. Plot them on a diagram and find their Cartesian coordinates. Okay, so in the first one, we've got r equals 3 and theta equals 0. Who can tell me what is the x and y coordinates for the first point? Who can tell me? Smash that chat button. Who can tell me? Come on. If r equals 3 and theta equals 0, what will the corresponding x and y coordinates be? We've got 50 people here. Come on. Light up that chat. Yes, Brendan and Nisa. Good. Okay, Tom. So that's not a difficult question at all. Okay, so let's do B and C, and I'm going to draw a picture for those ones. And I'll go back to my document camera. All right. So this is 13. Okay. So if r theta equals 3, 0, well, we want to be 3 units away from the origin and no rotation. So if I was drawing this, that's where my point would be. Okay, right there. That was easy, wasn't it? Okay, part B is a bit harder. So part B is the following. All right, where does this take us? Well, we want to be 6 units away from the origin, and we want to rotate in a anti-clockwise direction, 7 pi on 6. Okay, so 7 pi on 6 is just a bit more than half a turn, right? So that would be pi, and then you would have a little pi on 6 there. And this length here would be 6 units. Okay, so you know in this quadrant that both sine and cosine are negative. Okay, just give me a second. Oh yeah. Okay, so we've got this little triangle now. Okay, where you've got the hypotenuse is 6. This angle here is pi on 6, and you can just use trigonometry to work it out, right? So you don't actually really even need to use trigonometry, but you'll get this. Okay, so this is one of your basic triangles where you've got 30, 90, and 60 in it. Okay, so there are your coordinates for it. And what about part C? Well, let's draw that. So you go out 2 units and you rotate 7 pi on 4, which is almost 2 pi. So you go all around here and then you come back pi on 4. And this will be 2 units here. Okay. So who can tell me in the chat, what would the corresponding x and y coordinates be here? Who can tell me? Who can tell me in the chat? What are the x coordinates and what are the y coordinates here? Who can tell me? Come on, we've only got 7 minutes left. Nisa. Yeah, x is positive, y is negative. This is one of those equilateral triangles. So there you go. Great. Great work, everyone. Okay. Let's go and have a look at 15, because sometimes they'll ask you to sketch the graph corresponding to a polar equation. Okay, so these first ones are pretty easy. This one's a bit harder. Okay, so one of the ways you can do this is to draw them first on the the r theta axes, but I don't think you really need to do it in this case. So let me show you a way around that. So let me share my document camera. So let's consider this. Okay. So what does this mean? Well, it means that we are always 4 units away from the origin. And theta, there's no restrictions on theta. Okay. So can anyone tell me, what do you think this curve is going to look like? Can anyone suggest what this curve is going to look like? Yeah, Ning Shao, thank you. Can you say more? Yes, it's going to be a circle. What more can you say? Circle with radius 4, yes. Anything else? What about, where is its center? Thank you, Omar. Yes, that's it. Yes, Isabella, Nisa. Okay, so this. Okay, it's a badly drawn picture, right? But it is a circle a circle with radius 4 and center at the origin. Okay, that's nothing. Okay, let's do part B. Part B is an interesting one. Now it's a different equation. There's nothing about r here. We just told theta equals 2, and we're talking about radians here, right? We're talking about radians. So does anybody have any idea what the points on this curve, what this curve actually looks like? So we're fixing the angle here, but we're not saying anything about the distance to the origin. Well, one way is to say, okay, well, this is 2 radians, right? So we sort of go a bit more than half, and we're not limited by the distance. Okay. So let me just check something there. Okay. So my picture here isn't quite exact, right? I've drawn the whole line here, where actually I should have just gone. Okay, so it should really be half of that. Yeah. So you probably just want to cover that up. Okay, so I've sort of drawn too much there. Yep, you guys are on the right track there. So it is a ray in the second quadrant. Okay, so forget that. It's just that bit. All right, last one, part C. This one here, this is a famous equation. But what's going on? Well, let's look at the relationship between the distance and the angle theta. So as theta increases, the distance also increases. So what does this actually look like? Well, if theta equals 0, I haven't rotated, r0, so I'm actually here, right? If theta equals pi on 2, so I've rotated this far now, this will be 3 pi on 2, okay? If theta equals negative pi, I'll be out here, so this will be negative 3 pi. So what's happening here is this is getting bigger and bigger and bigger, okay? And it's a spiral. Okay, folks, that's a little bit yeah. I think this is defined. Okay, so firstly, should it be so Tin, are you talking about part C? Because I think we can include it here. Yeah, because when theta equals 0, r equals 0, right? So I actually haven't done that, right? So yeah. Okay, so Nicholas, So what's happening here, what I'm trying to do in part C is to like find out what the relationship is between these two things sort of geometrically, right? So here I've just started with theta equals 0 and I'm at the origin, right? And then what happens when like I go through this turn, okay? So when theta goes to say pi on 2, this will be 3 pi on 2. So I'm right here. This is the 3 pi on 2 on the y-axis. And then if I go another quarter turn, theta goes towards pi, right? So the distance will be 3 pi, which is on this axis, it's negative 3 pi, right? And then just keep going. And this, as this increases, this increases. Okay, Nicholas, are you? Is that kind of like doing it for you? Yeah. So what I try to do, I just try to say, well, what's happening as I vary theta? What's happening with the r? Okay, folks, time to go. From me and Quokka, we will see you next week. So namaste, enjoy the day, and good luck with lab test 2 next week. Don't forget about it. And I will see you all next week. I can't wait. Just have a great day. All right. Bye, everyone.